In this video, I'm going to be going through moment forces. Now, we've already learned about forces. We know that forces are a push or pull. There's something that causes something to start or stop moving. They can also be a twist. So we've learned about the terms for a pulling force is tensile force. Something that's squashing or pushing is something is usually a compressive force. But we also have other forces like shear force and torsion and bending that we may have talked about at some point already. We've also learned that force equals mass times acceleration. We've used vectors, with the addition of vectors to find forces, using things like the three-force method and finding equilibriums and resultants. What we're going to look at now is we're going to use these three rules. We're going to use these three rules to solve some questions where we have unknown values, where we have unknown forces. So we're going to go back to this example, the classic example we like to talk about with levers. And I'm going to say here that if I have a lever, and I'm going to say this is a 30 kilogram force, well, I can't have a 30 kilogram force, but if I have a kid who's sitting on here, a little kid who's 30 kilograms, what would the force be down?
300 newtons.
300 newtons, exactly right. Okay, now, the distance of this seesaw, just to make life easy, is we're going to say it's 1 meter. And this one here, we're going to use millimeters. I'm going to use meters. Okay, it's fine. I'm going to use, this one is 0.5 meters. Okay. What force would we need to balance this?
600 newtons, 1 force.
Okay, 600 newtons. So a kid who weighed 60 kilograms. Okay, how do we prove that?
Displacement.
Yeah, we just kind of know it intuitively. Right? We've talked about mechanical advantage. So we know that if this lever, if this side is half as long, well, the force is going to need to be twice as big. We know that work equals force times displacement. I think that's what you were saying before you said displacement. So in this case here, the distance that is being moved is half as much, so we need twice the force. Yeah, and that makes sense when we think about levers. But there are other ways that we can approach this. What we could say is there's some sort of turning force that's happening here. So what we can say here is this side, we have a turning force. Is it going clockwise, or is this making the beam, or the seesaw, is it making it go clockwise or anti-clockwise? If I push down on this side, anti-clockwise. Okay, so we're all okay with that. That's anti-clockwise. And what we can say here is that if it's force times displacement, or that's when we talk about work, it's going to be 600 times 0.5. And 600 times 0.5 is 300 Newton meters. On this side, it's going the other way. It's going clockwise. It's turning this beam clockwise. And we can say here is 300 times 1 meter equals 300 Newton meters. Okay, now that helps us to figure out what these forces are. There's another way we can do that. Before we get to that, I want to talk about the sum of the forces vertically. Now, in this situation, we figured out how to balance the lever, how to balance the seesaw. But these forces are unbalanced. There's something else that's going on here. So we can see that there's 603 to 300 newtons. There's newtons pushing down, but there's no force pushing up. And if there's nothing pushing up, we don't have an equilibrium. So how can we have an equilibrium? How can this balance, how can this push up without it?
Is that at the fulcrum?
Yeah, so at the fulcrum, there's going to be a reaction at the fulcrum. Okay, so I'm going to draw that there. That's a force, and I'm going to call that R for reaction. Okay, so we've got a reaction. So what we can do there is, what do we think that reaction force is going to equal?
600.
900. Okay, I like that answer of 900 newtons. Now, that just intuitively looks right, but what we're going to look at is how we can solve that. So, if we put this formula here that says the sum of the forces vertically equals 0. Now, when we have those three formulas, technically it's not always horizontal or vertical. The idea is that it's really sum of the forces in the y direction. But almost always we're going to use the sum of the forces vertically as our formula. So I will point out here that it really is technically sum of the forces in the y direction equals 0, and here it's sum of the forces in the x direction equals 0. But I'm not really, we're typically going to use vertical forces. Yeah. Okay, if something's not moving, I was trying to put it in silent, but hopefully you won't call back. If something's not moving, it's in equilibrium. That means all of the forces added together are going to equal 0. So what we've said here is that we've said up is positive. So if we go left to right, well, we start off with the 600 Newton force, and we've said, is it going up or down?
Down.
Down. So we're going to write minus 600 because it's down. We've said our convention is up is positive. And the next force we have is R. Now, is R positive or negative?
Positive.
Positive. We assume that it's positive. We assume that it's positive. So I always write a negative, and then because you can turn a negative into a positive, it's hard to go the other way around. So I'm assuming it's up, therefore positive. You don't need to write the stuff in green. I do so that you understand where things will come from. And then I have minus 300. Is it minus or is it not?
It's minus.
It's minus because it's going down. Okay, so that's a pretty easy equation to figure out, right? What we're going to do is we're going to say 0 equals minus 900 plus R. And then what we can do, I don't really need to do this, but I keep doing it, plus 900 plus 900. They're going to cross out. Therefore, what we're going to be able to say is that R equals 900. Now, I'm actually going to write with one extra step. I'm going to write, so if we add 900 equals R, R is positive. Yeah, we've proven that R is positive?
Yep.
So if R is positive, that means our assumption, positive, therefore our assumption was okay. If it's not okay, we usually write NG for no good. It's okay, therefore it is in fact going up. Our assumption that we made earlier was right. Again, you don't need to write that, but I find that that helps people. Therefore I can write R equals 900 newtons up. Yeah, it's important to write the direction on there. Now, that's one way of solving that reaction. But for me, what I would typically do is I would just typically draw a little diagram instead. I'd say, okay, that's 900, that's 600, that's 300. R equals 900. It's like a little scale drawing. It's obviously not to scale, but if I draw that, that just makes so much more sense to me. I just look at that and I say, oh, it's okay, some of the forces vertically, it all just makes sense. Now, when we were doing vector addition, what we were doing is we were finding the sum of the forces vertically. We were calling that the height of our rectangle. And when we were doing our vector addition, we were also doing the sum of the horizontal forces equals 0. That was the width of our rectangle. I just wasn't explaining it in those terms. Now, if I told you instead that I had, we're going to look at another beam in a second, we'll look at horizontal, trust me, we'll look at a horizontal beam in a second. But for the moment, that's how we find our vertical forces, some of the horizontal vertical forces. Me, I do this. I would still write this first line, some of the forces vertically, and then draw that little diagram. You can write this, but I almost never do. I just find it very unintuitive. I find that I get my signs mixed up. I just don't like to do it. Okay. So what we're going to look at now is we found this value. We kind of just did it intuitively. What we're going to look at is we're going to prove that this value here is actually is actually 600. So I'm going to call this instead, I'm going to call this B for big kid. Yeah? The force of the big kid, right? The weight of the big kid. So what I'm going to say here is I'm going to use this formula. The sum of the moments equals 0. What that means is the same way that the sum of the forces, all the vertical forces equals 0, and the sum of all the horizontal forces equals 0. What we also know is that sum of all the turning moments have to be equal 0. Now, what we're going to do is we're going to measure from a location. In this case, I'm just going to say here, I'm going to write down x. Just to say the point is, it doesn't matter where we measure. From any location, the sum of the moments are going to equal 0. But that doesn't make much sense here. We'll get there. Now, we said that with the levers, we used force times displacement to figure out the amount of work done. Well, moments are measured by force times perpendicular distance. It's kind of the same as displacement. You get the same idea. I don't need this today, so It is helpful to know where the end of that is. Okay, so otherwise it casts a shadow. Okay, so force times perpendicular distance. We'll worry about perpendicular distances later, but for the moment we're just going to say force times distance. Now, how am I going to write that working out? What I'm going to say is that I'm going to start off by establishing that clockwise is positive. Now, a lot of the time you'll see textbooks use anti-clockwise as positive. You'll see HSC questions use clockwise as positive. Both in my working life and at uni, I used anti-clockwise as positive a lot of the time. I think at high school we tended to use anti-clockwise as positive by default. Now, I decided when I started teaching that I decided for the sake of keeping things simple, I'm going to always use clockwise as positive 100% of the time. And I haven't looked back. 7 years later, here I am still using the same thing. Okay. This is the Greek letter sigma, the capital sigma, not to be confused with this little guy, right? That's for stress. This is for the sum. The sum means if we add them all up, yeah, the sum of the moments from any location equals 0. But we're going to choose a location. If we want to find B, what we have, let's imagine we don't have R yet. Let's assume that we don't have R. Just for the moment, let's just imagine that we haven't found R yet. Because we were able to find, we found R once we knew B, yeah? So, do you remember that? Yeah, we found R once we found B. We didn't go the other way around. So, let's assume that we don't know R yet. So, we have two unknowns. All we know is the weight of little kid. Little kid is 30 kilos. All right? So, under gravity, Earth's gravity, assuming we're on Earth, right, we just say 300 newtons. All we know is that. We don't know. Sorry?
We also know the two
We do know the distances. We do know the distances. Excellent. I was thinking that, but I'm glad you said that out loud to clarify. So, we have two unknowns. So, to be able to eliminate one of these unknowns, we're going to use a trick. What I'm going to say is, we're going to measure from this point. Now, I'm going to label this. We could label this R, right, for reaction. That's where the reaction's taking place. Or what did we call it earlier? We called it a fulcrum or a pivot. Yeah, I like either of those two letters. Maybe we could call this P, location P. And so I'm going to say, measuring everything from location P, all of the turning is going to equal 0. Okay, so let's see what that looks like. I'm going to say 0 equals, and I'm going to go from left to right. I just want to pick a consistent starting point, and I'm going to go from there. Now, for B, I have force B. I'm not worried about its distance yet. I just want to say, if I'm putting my finger on force P, and imagining this was a clock with a hand, if I was turning this little hand in the direction of B, if I went ding, 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 which way would the wheel spin? Anti-clockwise. And we've said clockwise is positive. So we're going to leave this as negative. Yeah, because it's anti-clockwise and anti-clockwise is negative. Okay, so it's B. What's the distance from B to P?
0.5 meters.
Yeah, 0.5 meters. Okay. We have another force. Right, this other force here. I'm going to write this in green to say you don't need to write this, and a lot of textbooks don't. And I think it's confusing that they don't. So I'm going to write it in green. Anything I write in green, you don't need to worry about. Okay. Well, in these equations, right? So now I'm going to write minus R. How far is R from P?
It's the exact same.
Which is, its distance is 0. Excellent. Oh, we got there really, really fast. That was amazing. Okay, the distance is 0. Yep. Okay, so effective. Sorry?
I was about to say, do you also have to add the 300 meters?
We do, we haven't finished. Okay. Then we have here, this one here, 300 is the force. So measuring from P, so I'm putting my finger on the axle. Barra, 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 clockwise. So I'm going to turn this into a positive. What's the distance from 1 meter? Excellent, you guys are already there. It's 1 meter from our reference point. Yeah, we've said our reference point is P, it's 1 meter away. Now let's write that in. We've got 0 equals 0.5b, oh, it's minus 0 equals 0.5b. Now, what about this one here? Anything times 0 is?
0.
Do you see why people don't bother writing it? They don't bother writing it. But I want to draw to the point to you. That's why we use this moment method. The reason why we solve things using the sum of the moments equals 0 is because if we measure something from P, the force disappears in our equation. It doesn't matter if this is 10 or 3 billion, right? It doesn't matter what the value is. If it multiplies by 0, it's 0. So we can just keep on going with our equation. It's great. Yeah, it's fantastic. It just eliminates that force. So we can keep moving. Okay, then we've got plus 300. Okay, so what I'm going to do here, I'm going to try to avoid doing this too often, but I'm going to say plus 0.5b plus 0.5b. Those cancel out, so what I'm left with is 0.5b equals 300. Right? Now, is that number positive? Do we have enough information at this point to say that that number is positive?
Yes.
We do. So I can write here, I can say positive. Oh, did we make any assumptions? We made an assumption about B. We made an assumption that B was down, so I'm saying down, therefore anti-clockwise. Yeah? Down, so I'm assuming down, therefore anti-clockwise. It was positive, therefore my assumption was okay, therefore it is in fact down. Yeah? So what I can say there is I can now say B equals, what I'm going to do is I'm going to divide both sides by 0.5, so I'm going to say 300 divided by 0.5, B equals 600 newtons, and we've found the direction is down. Yeah.
Way more complicated.
It is. Okay, so the comment, and quite rightly, this way is way more complicated. Why would anyone use this method? Well, for levers, okay, at this point it's pretty simple, right? I think for levers, this is a pretty intuitive thing. Why are we making life so difficult for ourselves? We're going to look at situations where it's going to be where we're going to have it be more challenging. So we're starting with something very simple, and then we're going to build up. Now, before I move on here, okay. Okay. Excuse me. Okay, so in this question here, what I'm going to say is instead of having the 30 kilogram kid, I'm going to have instead someone pushing the side of this lever. Yeah, instead of it being applied directly, what we're going to do is we're going to push it. Push on it. We're going to push on it, and we're going to say, I don't care what value we use. We're going to use the same weight. We're going to say, let's say it's 40 kilograms of force, which is going to be 400 newtons. Yeah. Now I have to give an angle. Right, I have to give an angle. So we're going to say 60 degrees, because generally what we're given is 60 degrees or 45 degrees. 60, 30 or 45. Now, if we're going to solve this question, well, there's two ways we could solve it. The first way is we can just replace this 40, we can replace this 40 with two other forces. Right? So what I can do is I can replace that 40. Let's see what it looks like if we replace 40 with two other forces. 40. I say 40, it's actually 400. Okay, so 40 can be replaced. We're going to break it into its components. If we break this into its components, what do we have here? We have 200, and the down is going to be what? Okay, so this is the angle. This is 60 degrees. So this is adjacent or opposite to the angle? Opposite. So this is going to be 400 sine 60. which is going to be equal to 400 brackets 0.866. You guys have calculators, can you tell me the answer?
346.4.
What is it?
One decimal.
What is it?
346.4.
346.4. Okay. And that's going to be going down, and this one's going to be going to the left. Okay. So what I can do now is I'm just going to temporarily, I'm going to replace that with two other forces. I'm going to replace it with the two components. So I'm replacing this with a force of 346.4, and this one here with 200. Now, in this situation, we've said that R is going straight up, but now this is where the sum of the forces horizontally come into play. Now, there has to be actually two forces to push back here. There needs to be R in the horizontal, and there needs to be R in the vertical, and then when we add those together, we'll get R total. Does that make sense? Great, okay. So, let's have a look at that. Okay, so what we're going to do is we're still going to take moments about P. Now, we could say, moments about P, we're going to start with 0 equals B. Now, which way is B? Following our convention, assuming that B is actually going down, right, what angle are we going to use?
90.
So it's 90-degree angle, but we're going to use, what, is it going clockwise or anti-clockwise? Okay, so anti-clockwise, so we're going to say minus B times 0.5. Okay, we've got all this nonsense here with R, but we don't care about any of it. Why don't we care about any of it?
Because it equals 0.
Because the perpendicular distance is 0, so R times 0. We could write RH times 0, RV times 0, but it's all going to be times 0, so we don't care. And then we're going to have minus 346.4. Is it minus? Plus. Okay. And what distance is it?
1 meter.
1 meter. Okay, what about the 200? What about the 200? What's the perpendicular distance?
Oh, is it going negative?
It's going, okay, so someone said it's going negative because it's going to the left like Beyonce. Yeah. What's its perpendicular distance? How far does it, let's do the thing. I'm going to put my finger on P. Is it going clockwise or anti-clockwise? Which way is it spinning the wheel?
Nowhere. Neither.
So its perpendicular distance is?
0.
Excellent, you got there. Okay, so I didn't write that in green because I wanted to trick you. Instead, what I'm going to do is I'm just going to box it in green to say you don't need to write this.
So we're assuming that, are we assuming that it's not spinning at all and also it's not moving at all?
This is not creating any turning moment.
Okay.
There's no, it's not creating a force that's going to cause this thing to spin.
No, but I mean, like, is B equal to the, so B's stopping it from spinning at all?
B is what's stopping it from spinning, yes.
Okay, so we're just assuming that's not, okay, right, I guess.
Yeah, this is not contributing to the spin of the thing. Okay. Now, if you have a cramp, you can go out to the, to sort yourself out. Okay. Let's have a look at the value of B under this circumstance. Yeah, because the load condition has changed.
Yeah, but yeah, we have a different number.
Okay, so 0 equals minus 0.5B plus 0, which we're not even going to bother to write, plus 346.4, right? That's what we've got. So we can then say B equals, so that's going to become a positive, B equals 346.4 divided by 0.5, and it's positive, so therefore our assumption was correct. We set up here, our assumption was that it was going down. Right, I'm not going to focus too much on that moment, but it is positive, therefore...
That's 692.8.
What was it?
692.8.
Yes. 692.8 newtons down. Okay, that's good, we've got that. We can write here B equals 692.8. Okay. Now, what about R? We were able to calculate R really easily last time, but what about now? R, well, first we're going to need to know RH. How are we going to find RH? We're going to say sum of the forces horizontally equals 0. Now, we could do the method I said before, but it's easy to see. How much left have we got? What are all the leftward forces on this diagram?
Just 200.
200. Right, we've got 200 that way. And then I have RH. So looking at that, I can pretty easily say RH equals
200. Would that be negative 200 then? Or just
to the right. Yeah. I didn't use positives and negatives. I just looked at my diagram and said, okay, for it to balance, it has to be that.
Okay.
Yeah. Okay. What about the sum of the forces vertically? Let's have a look. I've got 692.8 going down. I have 340. Oh, that's not 4. 346.4. That's also going down. So, what is my missing force? What have we got?
Oh, there's just
Okay,
then plus
346.4 plus
1,639.2.
I don't disagree with you, I just will be easier to write down. 1,039.2 newtons up. Okay, now if I had to give R total, how would I find R total?
Add them horizontal and vertical together.
Okay, I'm going to remove this part here, we don't need this anymore, so I'm going to remove this part. So we're going to say that R total, we're going to add the two components.
You have to do the square root.
Yeah.
And then get the square root both of them and then do the.
Oh, yeah.
Sorry.
Oh yeah, because it's
Okay,
That's the.
Square both of them and square.
so R is going to equal RV squared plus RH squared. R equals. Okay, vertical was 1039.2 squared. And the horizontal was 200 squared. Okay, so I've got this answer ready to go. I'm going to square it. I'm going to plus 200 squared. And then I'm going to take the square root of all that. And I'm going to get my answer R equals 1058.3. Does that make sense? Is that a reasonable answer?
Yeah.
Okay, what do I mean when I say that? It's like, this is the hypotenuse. Is the number the biggest?
Yeah.
Yes, okay, that's good. If it wasn't, we'd have worries. Yeah, if it wasn't the biggest, or if I got a number of like 2 million, I'd also be worried. I look at this diagram and think, okay, yeah, that makes sense. Yeah. Okay, my angle, how do I figure out my angle?
10.
What's the opposite angle? RV over RH. Oh, just read that again. Okay, so I'm going to start with 200 divided by, is this number going to be greater or less than 45 degrees? It's going to be less than 45 degrees.
That's the wrong way around.
Opposite over adjacent?
Yep.
Your opposite is the larger number.
Oh,
The
okay.
vertical's higher, so the triangle should be like.
Thank you. I drew this diagram here was wrong badly. Okay.
Yeah.
Excellent. No one likes being wrong on the internet. You take that back about Wikipedia.
So it's
I'll
not.
later talk to you about elephants. And then, okay, so page.
What affect the R?
Shouldn't it be?
That's the same.
Should be 60 degrees, right? Because equal and opposite to the other force. Wait, no. No.
Okay.
Yeah, so equal.
Black one.
because you got the other force in it.
Yeah.
So it'll be less. It's going to be less than 60. No, it'll be more.
79 degrees.
Yeah.
Yeah, but
Now-
I think there's more force.
Let me take you back for a second. We've all done 3-force method. How many forces are there on this beam?
3.
Are they concurrent?
Yes.
Yes. Somewhere these forces meet.
Yeah.
Once we've found a point of concurrency, we can then find this angle. We could have solved this using the 3-force method. So if you look at my questions on the 3-force method, and I talk about graphical or analytical solutions, if you didn't bring a protractor, this is how you'd solve that question. If you had a protractor, you could use the 3-force method and it would save you a fair bit of working out. In my opinion, that's the way I'd go. So if you look on YouTube, you'll see there's lots of questions that I solved both graphically and using the analytical or calculator method.
This is way better.
Okay.
Way better.
Hey, look, I can hear students saying this way is better, probably closer to the camera than me. But the fact is, a lot of students do not like using graphical methods, right? And that's understandable. If you like this way better, if it's more intuitive for you, go crazy. Enjoy this method.